of the twin paradox, the acceleration version comes in. The two observers are Mary and Botan. They both start off on Earth at the same age of 20 years old. Botan stays on Earth while Mary takes off in a ship traveling at 0.6 C. Her destination is a star that's 3 light-years away. Upon arriving, she turns around and returns to Earth, again traveling at 0.6 C. Time equals distance over velocity, so it should take 5 years for her to get there and 5 more to come back. If we graph Mary's position over time in Botan's reference frame, you might assume it would look like this. But the thing is, discontinuous changes in velocity like this aren't really possible. In reality, Mary would have to accelerate to turn around. Things are complicated further when you realize she also has to accelerate to get up to speed at the start and to slow down at the end. Thankfully, we can eliminate these last 2 instances by simply having Mary already moving at 0.6 C and only passing by Earth instead of staying. But the acceleration to turn around can't be eliminated like this. If the turnaround takes 1 year, then the total trip will be 11 years. It consists of 3 distinct sections: the outbound trip, the return trip, and the turnaround. Now we'll use the graph to calculate both of their ages. Since this is Botan's reference frame, she ages normally for all 11 years, making her 31 by the point of reunion. But Mary is moving, so she experiences time dilation. If we look at her velocity graph, we can see for 5 of the 11 years, she moves at constant velocity 0.6 c. In that case, the alpha factor is 0.8, which means she ages at 0.8 times the rate, and therefore only ages 4 years during the outbound trip, while Botan ages 5. For another 5 of the years, her velocity is negative 0.6 c, which is just the same thing but the other way. So again, Mary ages 4 years, while Botan ages 5. The turnaround is where things get complicated. Since Mary's velocity isn't constant, it means her alpha factor also isn't constant, so the rate at which she ages is constantly changing. In order to figure out exactly how much she ages, we have to take an integral, but I'll spare you the details and we end up with Mary aging about 0.93 years, while Botan ages 1 year. Combining these, we can see that when they reunite, Botan is 31 and Mary is 28.93. This makes sense so far, but what if we switch over to Mary's reference frame? If the situation is completely symmetrical, then the graph of Botan's position in Mary's reference frame should be exactly the same as before, just in the opposite direction. But the 2 sides aren't exactly equal. In Mary's reference frame, the star and Earth are both moving at 0.6 c relative to her, which means length contraction applies to not only the objects themselves, but also the distance between them. Using the formula, the distance is now only 2.4 light years, so we have to adjust for that. Also, since the distance is shorter, it now only takes 4 years to clear the distance, so we'll adjust for that as well. This means Mary will turn 24 when she reaches a star, making those 2 events simultaneous. Since they also happen in the same place, relativity of simultaneity tells us they must be simultaneous in all reference frames. So it makes sense that this is consistent with what Botan's reference frame predicted. The same reasoning also works the other way. In Botan's reference frame, Mary is 24.93 when she passes a star for the second time. So this must be true in Mary's reference frame as well, which saves us from calculating it again. With that, we now have the full graph of Botan's position in Mary's reference frame. Almost. You see, the amount of length contraction Mary observes actually changes as she turns around. At one point, it even reaches 0, in which case the distance from Earth to the star is the full 3 light years. This puts Botan further away at that time, which we have to account for. Now this graph can be pretty confusing to look at, but it makes more sense if we watch the animation in Mary's reference frame. Mary is stationary the whole time, but at time 0, Botan and the star move to the left. At time t equals 4 is the turnaround, during which the length contraction between them briefly goes away, putting Botan even further before it returns as they go back to the right. So the full graph of Botan in Mary's reference frame is slightly different compared to the graph of Mary and Botan's reference frames. But it's still qualitatively the same, where they both see each other leave at 0.6 c, then turn around and come back. So even without doing the calculations, we already know what should happen. Mary is stationary since it's her reference frame, so she ages normally and is 28.93 by the end. But Botan is moving the whole time, and therefore experiences at least some amount of time dilation, which makes her younger than 28.93 by the end. So again, it looks like one reference frame tells us Mary is younger when they reunite, and one reference frame tells us Botan is younger, so we still have a contradiction. But here's the key factor. Postulate number 1 only guarantees the laws of physics are the same in every inertial reference frame. It doesn't guarantee this for non-inertial, aka accelerating reference frames. In the example, the fact that Mary accelerates means her perspective is not an inertial reference frame. So the laws of physics, including things like the time dilation equation, are not guaranteed to hold. Photon never accelerates though, so her perspective is an inertial reference frame, meaning we can apply the equations as much as we want to see that Mary will in fact be younger. In this sense, it's the fact that Mary accelerates but Photon doesn't that breaks the symmetry and resolves the paradox. But there's still an issue. In Mary's own reference frame, she never even moves, and it appears Photon is the one who accelerates the turnaround. So why isn't this the correct interpretation? Well, to see why, we can actually apply postulate 1 in reverse. If the laws of physics behave weirdly, then it means you're not in an inertial reference frame. If we look at what Photon experiences during the 11 years, it's just business as usual, where the only way for objects to change their motion is if they're acted upon by a force. The same thing applies to Mary for most of the trip, but the turnaround is different. You're probably familiar with how in a vehicle that's slowing down, objects are flung forward. Well, Mary basically experiences a year-long version of that in her ship. Of course, in our reference frame, we know this to be a fictitious force, where the objects are simply maintaining their constant velocity. But if you attempt to take Mary's ship as an inertial reference frame, then this is just acceleration that comes from nowhere. This is of course inconsistent with the laws of physics in inertial reference frames, which is how we know that this isn't one. And in fact, there are other strange things in this reference frame too, like the fact that Photon appears to be moving faster than light at one point, and this is all because we're in a non-inertial reference frame. Anyway, the fact that Mary's reference frame isn't inertial is how we know her calculations can't predict what actually happens in her reference frame. But that raises the question then, what would Mary observe during the trip? Well, even though her reference frame as a whole isn't inertial, some segments of it are. The only segment where Mary accelerates is the turnaround, so that part is a non-inertial reference frame, but the outbound trip before and the return trip after both take place in separate inertial reference frames. This means we can apply the time dilation equation in each of those, after which we find that Photon only ages 3.2 years on the outbound trip and another 3.2 on the return trip, while Mary ages 4 years each time, totaling 8 years for Mary and 6.4 for Photon. Now we know from Photon's reference frame that at the moment of reunion, Photon is 31 and Mary is 28.93. Since these events are also in the same place, relativity of simultaneity tells us they're also simultaneous in Mary's reference frame, so the ages by the end should be the same as before. That can only mean one possibility. Photon ages the remaining 4.6 years during the turnaround, in which Mary only ages 0.93 years. This means Mary actually observes Photon aging faster than her in a sort of reverse time dilation. And in fact, this can be considered a rule of relativity, where accelerating observers will observe a reverse time dilation in whatever direction they're accelerating, with the effect being greater with further distance. Just like all the effects of relativity, this is something that's been measured and matches experimental evidence. But even still, using the twin paradox to derive a rule, and then using that rule on the twin paradox might feel a bit circular. So here's another way of thinking about it. During the turnaround, the sudden apparent change in the laws of physics can also be thought of as a force that suddenly appeared. Mary herself resists it due to the laws of her ship, but everything else, including Photon on Earth and the star, would appear to be accelerating due to the same force, making it uniform through all of space. If we take a page from general relativity, it tells us that fictitious forces in accelerating reference frames like this are actually equivalent to gravitational fields. And general relativity has an additional effect known as gravitational time dilation, where time passes more slowly further into a gravitational field and more quickly further behind. Applying this to the uniform field from before tells us that Photon ages more quickly, which is exactly what we see. Now technically, in general relativity, gravity itself is a fictitious force, which means Photon's reference frame on Earth isn't inertial either. And in fact, the acceleration due to Earth's gravity is about the same as what Mary experiences. However, unlike the uniform field that Mary observes, Earth's gravitational field gets weaker the further you go, as per the inverse square law, so it doesn't actually have a significant effect in this example. So In the end, no matter which reference frame you're in, the result is the same. When they reunite, Botan is 31 and Mary is 28.93. And the key factor that helped us realize that was the acceleration of the turnaround.